Hello everyone, welcome back. So now we're going to be going into the ideal gas equation of state. This is super important for a lot of our problems. Now the equation of state is simply a way I can relate my pressure, my temperature, and specific volume to any specific volume of any substance together. Now the best one you know is the ideal gas equation, which you see a lot, and it looks something like this. If you take in chemistry, you've probably seen this equation before. Now, just to make sure that we're all on the same page, let's look at this equation and see what everything stands for. So first off, R is the gas constant, and as a note, that is specific. It's specific to what other material you're looking at. How do I calculate it? Well, I use my universal gas constant, and I divide it by the molar mass of whatever I care about. Or in the case of air, you divide it by the average molar mass of air, which is pretty close to nitrogen. Whoop. Now, if you're wondering, like you didn't see it in quite this form, just know that there's actually a bunch of different forms of this. So I can have P per mole with R universal. I can have this one, which is what a lot of people know, is the whole PV equals nRT equation, though a lot of times N is a lowercase n for moles, depending on what textbook you're using. I can also have PV equals MRT, where I have the specific gas constant. So there's various ones. The one we're going to use the most in this class, is P lowercase v, which is specific volume, equals RT. That's the one you use the most. It's very, very helpful. And as a note, if I have an ideal gas and there's two states for a fixed mass, this one right here where we can relate those two states together is very, very helpful, because we can then tell if I have pressure and temperature change for one, how it's going to change the pressure and temperature of the other, or some combination of the two. Now, another question you might be asking yourself is, well, what is an ideal gas? Well, idealization is always a way of making things simpler on ourselves. Some gases act ideal in most cases. Noble gases, typically ideal situations. However, for real gases noble gases are real too, but gases you actually encounter like water vapor or air, it's really only doing that for low pressures and high temperatures or low densities. Air, typically an ideal gas. Water, not so much. And why is that? Well, because water vapor, the low density thing isn't really working for us, and typically we're not getting to this high temperatures as would make it easy for us. You're going to have a lot of issues with water vapor. And why do you care about water vapor? Well, water vapor in the air isn't doing much to mess up your equations because there's very, very little water there. Water vapor in a turbine is going to be horrible because it's at very, very high pressures, and the temperatures are high too, but just not high enough. Now, at those high pressures, our ideal gas assumption is going to get really bad errors. That's especially when we get close to saturated vapor line, because we're getting close to actually changing phase, and also the critical point at the top of the curve, that's up here, where I go from being a liquid to a gas all at one point. So water, you just don't want to use the ideal gas equation for in most cases. And what you'll do instead is you'll go to the tables. Now, here's one thing you might run into and be kind of confused by. Air conditioning applications, we don't even care about the water vapor. We still treat it as an ideal gas. And the answer, or the question to that is why? Well, I'm going to go ahead and give it to you because I don't think your textbook does a very good job of explaining why. So 1 atmosphere is way too high of a pressure for us to really be saying ideal gas assumptions for water at the very least. However, air is made up of mostly nitrogen. Okay, so that is the grand majority of it. Then we have oxygen. Then we have other gases, and one of those is H2O. There's just a little bit of water vapor in air. Now, because there's only a little bit of water vapor in air, we can learn about something called partial pressure. And partial pressure simply says that just like nitrogen is most of the gas, it's also most of the pressure. So if nitrogen is 70%, then its partial pressure is like 0.7 atmospheres. If oxygen is 20%, then its partial pressure is 0.2 atmospheres. And then so water's partial pressure is like 0.005 atmospheres. I'm making it really small, but either way, it has a very small partial pressure. When it comes to ideal gas equation, that's what we care about for this. So it works out just fine. Okay, get that out of the way. Just so you know, it's not really super important what we're doing right now, but you'll see it later on. Okay, but like I said, where we do use water vapor all the time is in steam power plants. And so in those cases, you can't use your ideal gas equations. You're going to have to go to the tables, okay? You need the tables if you're going to be in those applications. Now, if you stay on the path of aero, then you're not going to have to worry about that too much. If you stay the path of mechanical, you're going to see it quite a bit. Either way, tables are important for this class as well as future ones, so make sure you're understanding how you use those tables. Thank you so much. I'll see you all next time. Bye-bye.